For section 7.3, we're going to look at systems of linear equations in two variables. I absolutely love systems of equations. I think they're super fun. Hopefully you do too. We'll see. All right, so first of all, we need to review something. So in the previous section, section 7.2, we talked about linear equations in two variables, okay? So let's just kind of quickly remind ourselves what a linear equation in two variables is. So a linear equation in two variables is any equation of the form ax plus by equals c, where a, b, and c are real numbers such that a and b are not both zero at the same time. Okay. And in that section, we talked about two different types of equations. Okay. We talked about standard form, which is that ax plus by equals c. We also talked about slope-intercept form, which is y equals mx plus b. And I didn't list it, but I probably should have. We also talked about two other forms. We talked about x equals a, where a is the x-intercept. This was a vertical line. And then we talked about y equals b, where b is the y-intercept. This is a horizontal line. And then there is another format, which is y minus y1 equals m times x minus x1. This is explicit, well, I don't want to say explicitly. This is typically used to find the equation of a line. This is called point slope form, and we don't really have to cover this one, okay? So this one is not kind of in our curriculum, okay? So not in Math 143. Okay, the other four we've seen. All right, so we need to kind of remember all of that because it leads us into this idea of a system of linear equations in two variables. So that is our first topic. What is a system and what do their solutions look like? Okay, so we have a couple of definitions. The first definition is that of a system. So a system of linear equations, specifically in two variables, is a set of two or more, for us, it's going to be two equations that are solved simultaneously. Okay, so you could have a system of three equations, three variables. You could have all sorts of systems where you're modeling real world stuff, where you have systems in, five equations, two variables. You could have crazy stuff. For us, it's just going to be two equations. Well, let me not mark out linear. There. It's just going to be two linear equations that are solved simultaneously. So we're going to have two equations and two variables that we solve at the same time. Okay. So what in the world would the solution be? Okay. Well, the solution to a system of equations is the ordered pair that satisfies both equations. Okay, so that kind of makes sense. When we're looking for solutions to just a regular equation, we're looking for all of the ordered pairs that satisfy that equation. So if we're looking for the solution to a system, we're looking for the ordered pair that satisfies both equations at the same time. Well, what would that be? Okay, for us, this is the ordered pair that represents the point where the two graphs intersect. Okay, and that's not just for us. I mean, that's the solution. So when you're looking at a system of linear equations in two variables, you're looking at two equations that you solve simultaneously, and the point of intersection is the solution. Okay, so we're looking for the point where the two graphs intersect. Okay, so there are really three ways that we can solve these. We can solve by graphing. We can solve using two algebraic methods, one called substitution, one called elimination, and we will have a video learning each of those methods. Okay, for now, what we want to do is we just want to test to see if the ordered pair that we've been given is or is not the solution to the system. So remember, we're looking for a single ordered pair that satisfies both equations at the same time. Graphically speaking, that is the point of intersection. Okay. So example one here says, determine if the ordered pair is the solution to the system. So you've been given a system and you've been given an ordered pair that could potentially be the solution. How in the world would we determine if this is or is not the solution? Well, all we have to do is take that ordered pair and plug it back into both equations. And if that ordered pair satisfies both equations, then we can say, hey, this is the solution. And we can back this up using Desmos. However, I've given you this disclaimer before with Desmos. Desmos is a wonderful tool. And if you use it appropriately, it can help you learn. If you let Desmos do all the work for you, you are absolutely cheating, okay? Desmos is there to verify solutions for us, to verify stuff, not to do the work for us, okay? So let's look at part A. We have the system 2x plus 3y equals -5 and 7x minus 3y equals 23. Notice here we have two equations and two variables, and we have this like giant curly brace that is in front of them. We'll typically do that to indicate to the reader, hey, we're talking about a system. These two equations go together, okay? So we want to check the solution. So let's check the first equation. So we're going to check 2 -3 and 2x plus 3y equals -5. Okay, so what this tells us is, remember, ordered pairs come to us x comma y. So the first number is the x coordinate, the second number is the y coordinate. And what we want to do is anywhere we see an x, we want to replace it with a 2. Anywhere we see a y, we want to replace it with a -3. So I get 2 times 2 plus 3 times -3 equals -5. We just have to use the order of operations on the left and see if we can get it to simplify to equal -5. So let's see, 2 times 2 is 4. 3 times -3 is -9. So I'm going to write this as 4 minus 9 equals -5. And then 4 minus 9 is -5. So we do get that -5 equals -5. So this is true. So the first equation checks out. But for this ordered pair, 2, -3, to be the actual solution to the system, it has to also satisfy the second equation. So we're going to check 2, -3 again, but we're going to check it against 7x minus 3y equals 23. So anywhere we see an x, we're going to replace it with a 2. Anywhere we see a y, we're going to replace it with a -3. So we get 7 times 2 minus 3 times -3. We want to know if that equals 23. Well, let's see here. 7 times 2 is 14. -3 times -3 is 9. So I'm going to write that as plus 9 equals 23. And 14 plus 9 is 23, which does equal 23. We get a true statement. This ordered pair satisfies both equations, meaning when we plug this ordered pair into both of those equations, we were left with a true statement. So we would say, yes, this is the solution. All right, let's try part B. So part B, we have the system 5x plus 3y equals 2 and x plus 4y equals 13. And we want to check the ordered pair -5, 9. All right, so we're going to check that ordered pair against the first equation. So anywhere I see an x, I'm now going to replace it with a -5. Anywhere I see a 9, or anywhere I see a y, I'm going to replace it with a 9. Bless my heart. All right, so we get 5 times -5 plus 3 times 9 equals 2. So I've just replaced x and y with -5 and 9. 5 times -5 is -25. And then 3 times 9 is 27. And -25 plus 27 is 2. So this ordered pair does satisfy the first equation. Let's check to see if it satisfies the second equation. So we're going to check -5, 9 against that first or the second equation. So that's x plus 4y equals 13. So anywhere I see an x, I replace it with a -5. Anywhere I see a y, I replace it with a 9. So let's see, -5 is just -5. And then 4 times 9 is 36. So I'm going to write that as plus 36 equals 13. And -5 plus 36 is 31, which does not equal 13. So it satisfies, this ordered pair satisfies the first equation, which means that it's a point on that line. It is not a point on the second equation. So we would say, no, this is not the solution. All right, so let's go to Desmos and see how we can work with systems, okay? So I don't have the physical worksheet in front of me, so let me take pictures really quick so I can remember what these equations are. All right, so 1, 2. Okay, let's go to Desmos really quick. So when you go to Desmos, you can type equations in standard form, slope-intercept form, anything. If you're looking for a table of values, you really do need to write the equations in slope-intercept form, but that's not what we're doing. Oh, whoops. So we can just type the equations in as is. Why is it not switching screens? There we go. Okay. All right. So for the first system, we had the equations 2x plus 3y equals -5. And then we had the other equation was 7x minus 3y equals 23. And we're looking to see what that point of intersection is. So this point right here is the point 2, -3, which is the ordered pair that we were asked to check on our example 1, part A. Okay, so you can see here the point negative or the point 2, -3 is the ordered pair where those two lines intersect. Okay, so let's look at the second part. So example 1, part B, we had 5x plus 3y equals 2. That was our first equation. Our second equation was x plus 4y equals 13. Okay, when we look at this point of intersection right here, we get this crazy answer. We get -1.82353, comma 3.70588, which is certainly not -5, comma 9. Okay, so let's look to see what -5, comma 9 really does look like. So -5, comma 9. All right, and it plots it up here. I didn't have it label it, but you can see it plotted this point way over here. So this is the ordered pair, -5, 9. You can see it is a point on that first equation, which is what we got. We got that this was a solution to the first equation, but you can see it does not touch the second equation. So this is why we could not say that -5, 9 was a solution. It satisfies only one equation, not both. For it to satisfy both equations, it would have to be this point of intersection. Okay? So that is how you can use Desmos to check to see what solutions are, but you should not let Desmos do the work for you. You are still expected to show algebra on paper. Desmos is merely a tool to kind of verify results, okay? In the next example, we will look at the first method for solving systems of linear equations in two variables.